So, our goal, as I mentioned last time, is to take an arithmetic function and define what we called the Dirichlet series corresponding to it, which is absolutely convergent in some half plane. So, let us say it is absolutely convergent when real part of S is greater than some sigma sub 0. Okay. And typically, we write sigma S as sigma plus IT, and we use the notation sigma for the real part of S. So, henceforth, whenever we talk about Dirichlet series, we proved last time that there certainly is a half plane in which it absolutely converges. So, we take sigma greater than sigma 0 to be that half plane where it converges absolutely. And our goal is to learn to study these Dirichlet series as an analytic function in the half plane where this series converges absolutely. So, this is something that we are building up towards. But just by virtue of absolute convergence, we can say a lot of interesting things about these series. So, let me briefly review something that we mentioned last time. So, let us do the following. Let us take some C which is greater than sigma 0. So, what happens is, since this series is absolutely convergent in the region, in the half plane where the real part is strictly greater than sigma 0, what it means is that it is absolutely convergent when real part of S is greater than or equal to C. That follows. So, all we want is, we want a half plane where the series is absolutely convergent, including the boundary of the half plane. So, we take C to be such a number which is greater than sigma sub 0, and last time we saw that if you take the sum f of n over n to the s, take any tail of this sum starting at some natural number n. Now, you know that this is less than or equal to summation n going from capital N to infinity absolute f of n over n raised to the sigma, and what we do is we write this as n raised to the sigma minus c plus c, which furthermore what we do is we take n raised to the sigma minus c outside with an upper bound, which is, since the sum is starting from capital N, so we have 1 over capital N raised to the sigma minus c, and you are left with absolute f of n over n raised to the c, which we know this sum converges. In fact, so for any fixed n, we are not going to take capital N go to infinity. You can fix any capital N of your choice. What you know is this upper bound. So, you are writing this series in terms of an absolute quantity 1 over capital N raised to the sigma minus c times a series which converges since C is in the domain of absolute convergence. Okay. Now, this is very elementary, but it has some interesting consequences. So, we now prove what is called the uniqueness theorem. So, here is this situation. Whenever you have two arithmetic functions which are equal to each other at every n, then clearly their corresponding Dirichlet series will also be the same. Now, but suppose you have two different Dirichlet series which in the region of absolute convergence converge to the same limits. So, let us take two functions defined on the set of natural numbers such that summation n going from 1 to infinity f of n over n to the s and summation n going from 1 to infinity g of n over n to the s. These are both absolutely convergent in the half plane sigma greater than sigma 0. Let us call this series, either you can call it LSF, or let us give them the name capital F of s and capital G of s. Now, I am not going to assume that f of s is equal to g of s everywhere. Okay, I am just going to assume, suppose there exists a sequence Sk, which you write as its real part, okay, in such a way that sigma sub k goes to infinity as k goes to infinity. So, suppose we have a sequence of complex numbers where the real parts are going to infinity, such that in the sequence the values of f and g match. So, capital F of s sub k is equal to capital G of s sub k, okay, for every element in the sequence. And your sigma k's, they lie in the domain of absolute convergence. Okay, all the anyway, the sigma k is going to infinity. So, obviously, beyond a certain stage they will become greater than sigma 0. So, without loss of generality, we are assuming that for every k, sigma sub k is greater than sigma 0. So, in this situation, if this be true, then f of n has to be equal to g of n for every n. So, all you want is the equality of the Dirichlet series for a sequence with real parts becoming larger and larger. That is enough for you to ensure that the corresponding arithmetic functions from which the Dirichlet series were constructed are equal to each other. So, this is called the uniqueness theorem, and this is a very nice consequence of the elementary inequality that we have written here. So, how does this work? So, let us take h of n is equal to f of n minus g of n, and let us say that our assumption, what we want to prove, let us assume to the contrary. Okay. So, suppose there are some natural numbers for which h of n is not equal to 0, and let capital N be the smallest such number. So, suppose capital N is the smallest positive integer such that h of n is not equal to 0. So, now what we do is note from the hypothesis of the theorem, what you know is that capital H, define h of s to be equal to capital F of s minus g of s in the region of absolute convergence. So, what we know is that by the hypothesis of this theorem, h of s sub k is 0, okay, for all the sk's with your real parts going to infinity. Now, from your lemma 2, from this inequality that we wrote here, what do we have? Note also that first of all, what really is h of s? So, what we do is we partition it into two parts. So, we first write it as this infinite series n going from 1 to infinity of your f of n minus g of n over n raised to the s, which we have also denoted as h of n. But now, by our assumption, for anything strictly less than capital N, this is just, the numerator is just 0, and therefore, the sum is starting from capital N. And now, by applying this inequality to h of n, what do we have? Also, if we take absolute of h of n raised to the, so what this is giving you is that this is certainly less than or equal to right. In fact, not just capital N, it has to start from capital N. So, we have this, and therefore, what does it tell you? This is just absolute of h of s, which you are saying that it is less than or equal to this quantity, and therefore, we also have h of s sub k is equal to 0, and therefore, h of s sub k, when you have, so what we do is we take the first term in the series out and have the remaining series from capital N plus 1 to infinity h of n over n raised to the s sub k is equal to 0, right. And therefore, h of n can be written as minus n raised to the s sub k times summation n going from n plus 1 to infinity h of n over n raised to the s k. And now, what we can do is that this inequality here, we can actually apply it for capital N plus 1. Okay. So, this therefore, absolute of h of n is certainly less than or equal to absolute of n to the s sub k, which is just capital N raised to the real part of s sub k times the absolute of this sum, which we know from our previous inequality can be written as 1 over n plus 1 raised to the sigma k minus c n going from capital N plus 1 to infinity absolute h of n over n raised to the c. Okay. Here, what are we assuming? Since we are taking a sequence sigma k going to infinity, for any c, there will be some k, so the sigma k is become greater than c, right. So, here we are just taking sigma k greater than So, basically except for possibly at most finitely many terms in the sequence, all the terms have real part greater than C, and that is the part that we are going to be considering. Now, note the following. So, this implies that absolute H of capital N, which we had started off with the assumption that it is not equal to 0, but now you are telling me that this is less than or equal to n over n plus 1 raised to the sigma sub k times n plus 1 raised to the c. So, we are just taking this to the top, and you have another sum which you know is a finite sum. So, for capital N, what are we getting? For a capital N as chosen here, we derive that it is less than or equal to this quantity, okay, with your sigma sub k going to infinity. But if sigma sub k goes to infinity, since this is less than 1, this part is going to 0, and this is just something absolute, some absolute bound here. Therefore, what you have is that this goes to 0, which means that H of n is forced to be 0, which is a contradiction to our assumption. And therefore, this tells us immediately that our assumption was false, and therefore, you cannot take any such smallest positive integer for which H of n is not equal to 0, and therefore, this has to be universally 0. So, this is this tells you that f of n is exactly equal to g of n for every n. And from this, we deduce the theorem that we had alluded to at the end of the previous lecture, which was that a Dirichlet series which does not vanish at some point on the complex plane will have an entire half plane of non-vanishing. Okay. So, this theorem states that, let us take, so capital F of s is just summation f of n over n raised to the s, okay, and as always we assume that the real part is greater than sigma 0, where the series is absolutely convergent. That is our universal notation. Now, we assume that, suppose there is some complex number s prime at which this Dirichlet series does not vanish, it is not equal to 0 for some s prime where the series is defined. So, the real part is greater than sigma 0. If this happens, then there exists a half plane sigma greater than c, where c is something greater than sigma 0, in which your capital F of s is not equal to 0. How do we prove this? Well, let us assume to the contrary. Suppose there is no half plane of non-vanishing. What that means is, whatever half plane you choose, to the right of that half plane you can find some complex number where this f of s does not vanish. Okay, now what you do is take a sequence of natural numbers k equal to 1, k equal to 2, k equal to 3 and so on, assuming to the contrary of what we want to prove means that for every such k you can find some sigma k which is greater than k, and in the half plane consisting half plane to the right of sigma sub k you have some vanishing point. Okay. So, but your sigma k's are now going to infinity. So, you have a situation which corresponds exactly to the previous theorem. So, you have a situation where f of s sub k is equal to 0, which in turn is the Dirichlet series coming from the 0 function. So, you have some infinite sequence sigma sub k, so that s sub k, so that f of s sub k is equal to 0 of s sub k in that sequence, and therefore, by the uniqueness theorem what that tells you is that f of n will have to be equal to 0 in that region. So, this means that, so proof, assume to the contrary, I am not going to write the whole thing again, by the uniqueness theorem applied to capital F and the 0 function, you end up getting that little f of n is equal to 0 for every n, which again is a contradiction, because you are starting off with a function where the Dirichlet series is not vanishing in some point. Therefore, you cannot have f of n to be equal to 0 for every n, all right. So, therefore, this theorem, as I indicated last time, tells you that there is a half plane of non-vanishing of a Dirichlet series, of a non-trivial Dirichlet series, that is a Dirichlet series which is not 0 everywhere. There will be an entire half plane where it will not vanish. Okay. So, so much for absolute convergence. We will later also talk about learning to treat capital F of s as an analytic function. So, we will, from absolute convergence, we will go towards uniform convergence in closed regions lying inside these half planes. But before that, just by virtue of absolute convergence, you can derive very beautiful properties of Dirichlet series, and that is what we are going to do. So, we are going to talk about Euler products. So, we want to be able to write our Dirichlet series in terms of infinite products. Now, before starting a discussion of Euler products, let us first briefly review infinite products. Okay, so, we have a general scenario in which you have a sequence of complex numbers. Now, typically, so far we have been talking about series of complex numbers. Now, we are going to be talking about products of complex numbers. So, let us take, just like you have sequence of partial sums, you also have sequences of partial products. So, let us take P sub n and define it to be k going from 1 to n alpha sub k. We say that the infinite product, so which we denote as summation k going from 1 to infinity of alpha sub k, we say that this infinite product converges if the corresponding sequence of partial products converges, but to something non-zero. If the sequence P sub n converges to some alpha in C where alpha is not equal to 0. If the sequence of partial products either diverges or converges to 0, then we say that the infinite product diverges. In particular, if the limit is 0, we say that it diverges to 0. Okay, that is because when we are relating infinite products, you may have studied this in your complex analysis course. When you are relating infinite products to infinite sums, you have to play with the logarithm function and you want to avoid the 0 case. So, naturally now when you talk about convergence of infinite products, you can also talk about absolute convergence of infinite products. So, without giving you detailed proofs, let me write down a few fundamental facts which you can verify yourself. So, first is, these are analogues of things that we learn when we talk about infinite sums. So, first is if the product converges, then the sequence of the partial products is converging to 1. In fact, not just P sub k, the limit of the alpha sub k's is equal to 1. Now, typically what we do is we study, so therefore, the kind of products that we will be looking at would be of the form 1 plus a suitable, we will write them in the form of 1 plus something. So, if product k going from 1 to infinity 1 plus a sub k converges, then the limit of a sub k as k goes to infinity has to be equal to 0, since the limit of 1 plus a sub k has to be equal to 1. Fact, so this is the first elementary fact. The next one is, if you have, in particular, if you have a sequence of non-negative real numbers and you are talking about their infinite products, then so suppose you have a sub k is greater than or equal to 0 for every k, then what happens? The product 1 plus a sub k converges if and only if the sum of a sub k, the infinite series coming from a sub k, also converges. So, this is how you show the equivalence between absolute convergence of infinite products and corresponding absolute convergence of the infinite sums. Okay. So, clearly, since here we are talking about a sub k greater than or equal to 0, we can take any sequence of complex number a sub k and talk about convergence of 1 plus absolute of a sub k. So, the definition of absolute convergence of an infinite product is product 1 plus a sub k, and here since we want the product to converge to something non-zero, we will always take a situation where your a sub k is never equal to minus 1. So, the product is said to be absolutely convergent if the product k going from 1 to infinity 1 plus absolute a sub k is finite. Okay. And this tells us from the previous fact that we wrote that, and to say that 1 plus a sub k is absolutely convergent is equivalent to saying that the sum a sub k is absolutely convergent. This equivalence is important for us when we start talking about Euler products. So, now we are ready to study Euler products. One other observation, just like absolute convergence of a sum implies convergence of the sum, similarly absolute convergence of a product implies the convergence of that product. With these facts in place, we quickly introduce the notion of Euler products, and henceforth our products, our infinite products will be running over primes. You have already learnt that there are infinitely many primes. So, here is the theorem that we want to prove. It is called the theorem. Usually whenever you apply this theorem, you just say by Euler product. So, what does it say? So, you have to start with a multiplicative function. So, let f of n be a multiplicative function which is not identically 0. Okay. So, I am taking a non-trivial multiplicative function. What does this mean? Before I continue with the theorem, a small remark. Remember, if you have a multiplicative function, then f of 1 is equal to f of 1 times f of 1, since 1 is 1 times 1, and therefore, it means that f of 1, so you bring them to the same side, it means that f of 1 is equal to 0 or f of 1 is equal to 1. Now, if f of 1 is 0, by multiplicativity the function would become identically 0. So, if you are assuming that your function is not identically 0, that means you are assuming that f of 1 is equal to 1. Okay. So, that is in this scenario. Suppose you are starting with the multiplicative function such that the corresponding sum of the values at every natural number is absolutely convergent. So, we are not talking about Dirichlet series yet, we are writing something more general. So, if you just have a multiplicative function such that the values, the sum of the values are absolutely convergent, then If this be the case, then summation n going from 1 to infinity f of n can be written as an infinite product over primes. Okay, and what is each factor? Each factor is of the form 1 plus f of p plus f of p square and so on. This is an infinite sum corresponding to the values of the function at prime powers. So, for each such prime you consider such a sum, and the product of all these terms will actually end up giving you the infinite sum. Now, to prove this theorem, what are some of the things we have to verify? First thing, we have to verify that this product that on the right hand side that we have written is indeed convergent. It is an infinite product that converges. This is the first thing you have to verify, and then you have to verify the equality with this. And what this theorem is telling you is that to check the convergence of the infinite product, the condition that your f of n's form an absolutely convergent series is sufficient. So, first thing we want to prove is the absolute convergence of this product, which in turn would imply the convergence. So, here is the proof. Note that for any prime p. So, since summation is finite, what does it mean? If you take summation of absolute f of p raised to the k, as k goes from 1 to infinity, you take this sum, okay, call it a sub p corresponding to any prime p. Define the term a sub p as the sum coming from the powers of that prime, but note that the summation, so each a sub p is also finite, right. And if I sum over all the primes and take a sub p, this will also be finite. Okay, this will be finite because of the finiteness of the sum. So, why is that so? So, this is equal to summation running over all the primes p. In the inner sum, what do you have? Summation k going from 1 to infinity f of p raised to the k. This is certainly less than or equal to sum over all the primes and sum over all the natural number k's, absolute f of p raised to the k, which is clearly less than or equal to sum, because all I am doing is I am only taking those n's which are powers of some p, right. So, this is, since this is finite, this tells us that your sum of a sub p's, the a sub p's form an infinite, form an absolutely convergent sum, and therefore, the product, okay, I should not have erased it, therefore, the product 1 plus a sub p as you run over all the primes is absolutely convergent and therefore convergent. So, we have, that is the product P, okay, of 1 plus summation k going from 1 to infinity f of p raised to the k is convergent. Now, we want to show that not only is this convergent, but in fact, this is equal to the sum of f of n's, all the f of n's. So, how do we do that? Note also that, so now what we do is, now consider what do you mean by the convergence of an infinite product? It means the sequence of the partial products converges. So, now what you do is define this to be, consider the following: capital P sub x, define this to be the product of all the primes up to x 1 plus f of p plus f of p square and so on. What you have is that this is a finite product, this is a product of finitely many sums, each of which is absolutely convergent. Therefore, rearrangement of sums when you are talking about p sub x is allowed, right. So, now what we do is, let us try to actually understand what are the terms in this finite product. So, arrange them as following. So, let us define a sub x to be equal to all those natural numbers x such that if they have a prime dividing, if any, all those natural numbers whose prime factors are bounded above. So, not just n less than or equal to x, what we need is all those n's. So, Jishu, this is the equivalent of this L infinity term you were studying in the paper of Jung and Sardari. Okay. So, all those n's such that if p divides n, then p is less than or equal to x. So, this is a much bigger set than all those natural numbers which are bounded above by x. It could have numbers which are bigger than x as well, but each prime factor of that n has to be less than or equal to x, and it also includes 1. We have to treat 1 separately since it does not have a prime factor. So, let a sub x be this set. Then your p of x, like we said, you have a product of finitely many sums, each of which is absolutely convergent. So, these can be rearranged, and after rearrangement you can easily write p of x as summation n lying in a sub x f of n. And so, when you take sum f of n going from 1 to infinity and remove p of x from it, what are you left with? You are left with all those n's which are natural numbers, but not lying in a sub x f of n. This is less than or equal to summation n lying in n minus a sub x absolute f of n. But notice that if n does not lie in a sub x, okay, then what happens is that, So, if n has at least one prime factor which is strictly greater than x, that means that n itself is greater than x. But what do you know about this? This is a tail of a convergent, absolutely convergent series, and so therefore, this goes to 0 as x goes to infinity. Therefore, as x goes to infinity, this difference is going to 0, and this tells you that your infinite product over primes is exactly equal to the infinite sum that you have started off with. Thus, summation n going from 1 to infinity f of n is equal to product over all the primes 1 plus f of p and corresponding to each prime p, this sum very frequently it is called an Euler factor. So, you have an Euler product over all the primes, and for each prime this is the corresponding Euler factor. So, now you know this equality. This is something that it lies at the heart of the study of multiplicative functions. And how do we apply this to the scenario of Dirichlet series? So, therefore, corollary, suppose you have a series f of n over n to the s, which is absolutely convergent in the region sigma greater than the half plane sigma greater than sigma 0, then you can just replace f of n by f of n over n to the s. This is also a multiplicative function, and therefore, what this tells you is that summation. So, in this domain of absolute convergence, this is equal to the infinite product of Euler factors and so on. Okay. If sigma is, all of this is valid only in the region where this Dirichlet series converges absolutely. So, now by the way, a quick observation. If you had even a nicer function, if f were completely multiplicative, suppose you had for all n and m, then you can simplify the Euler product into something even nicer. What is that? So, f of p square can be written as the square of f of p cube can be written as cube of f of p, and so on. So, this just becomes a geometric sum with ratio f of p over p to the s, and therefore, your with the same conditions as above, this turns out to be equal to the infinite product over all the primes 1 minus f of p over p to the s inverse. In particular, the easiest, the most immediate completely multiplicative function that we can take is that which is just equal to 1 everywhere, and in that case your corresponding Dirichlet series is the zeta function, and you have a corresponding Euler product for the zeta function. So, now that we have studied these sums and products rigorously as complex analytic objects, well, we have not gone all the way and discussed them as complex analytic functions yet, but as absolutely convergent products and series. That itself tells us a lot. So, now let us go to examples. So, as I just mentioned, zeta of S, which is the infinite sum n going from 1 to infinity 1 over n raised to the s, can be written as the Euler product over all the primes 1 minus 1 over p to the s inverse, provided your sigma is greater than 1, because that is the half plane in which the zeta sum converges absolutely. Next example, it's a very interesting example. This is the infinite series constructed from the Mobius function. So, let us consider mu of n over n to the s. Now, this is absolutely convergent. You can verify when the real part of sigma is greater than 1, just like above, since absolute mu of n is at most 1, right. So, therefore, what that means is that in this region where it converges absolutely, the sum n going from 1 to infinity mu of n over n to the s can be written as the infinite product of over the prime. Now, what are the Euler factors corresponding to each prime? 1 plus mu of p over p to the s, p being a square free number with just one prime factor, mu of p is just minus 1. What is mu of p square? Mu of p cube, mu of p to the a for any a greater than 1, it is just 0 by the definition of the Mobius function. Therefore, the Euler factor does not go beyond the first term. This is your Euler factor. And how do you compare it with the one that you obtained above? This had inverse, this is just what it is, and therefore, this is exactly equal to 1 over zeta of s when real part of s is strictly greater than 1. So, another interesting Dirichlet series. Let us write another example. Let us take the function d of n, which is the sum of divisors function, and you have verified on previous occasions that d of n is a multiplicative function, not completely multiplicative, but a multiplicative function, and therefore, your d of n over n to the s can be written as the Euler product, where, so you have 1 plus, what is d of p, the number of divisors of the prime function, positive divisors, is just 2. What is d of p square? 3. And so on. So, in particular, corresponding to any p raised to the ks, you will have d of p to the k in the numerator, which is just k plus 1. And the amazing thing is that you can, there are different ways of checking this. You can actually write this as a product of the zeta function with itself. If you have an absolutely convergent series, then in the region of absolute convergence, you can talk about products of those series as well. Okay, but how to see that? So, this brings us to the final topic for today, which is the multiplication of Dirichlet series. So, what we have is, let us take capital F of S for sigma greater than, let us say, some sigma sub A. This is the region where it absolutely converges. Let us take G of S to be another Dirichlet series What that means is that if you take the maximum of sigma A and sigma B, then you can have that the product of so in that region, both you know that both F and G would absolutely converge when sigma is greater than the maximum of sigma A comma sigma B. So, thus for sigma greater than maximum of both F and G converge absolutely. Therefore, we can talk about their products, and you can, when you do the products, you can rearrange their terms, right. Rearrangement itself tells you so many beautiful properties of a Dirichlet series, right. So, capital F of S, G of S, what is this equal to? So, you have summation n f of n over n to the s times, let us say, you are taking this product. So, when you bring together, what you have is basically a double sum over n's and m's over n times m raised to the s. This is a double sum, and therefore, what it means is that, so basically you can write this as 1 over k to the s, and corresponding to each k you are taking all possible factors. Okay. So, all possible d dividing k f of d times g of k over d. This is just a rearrangement of your product, and this is what is called, this sum is called the convolution function of two arithmetic functions. So far we have not used, and we do not need multiplicativity over k to the s, we just need two functions. So, this is why the notion of Dirichlet convolution is important. So, for f and g, two functions which are arithmetic functions, the function, the convolution is defined as, you run over all the positive divisors of n and take f of d times g of n over d. This is your Dirichlet convolution, and we just saw the use of Dirichlet convolution. It helps us to give the coefficients for products of two absolutely convergent Dirichlet series. Now, some quick examples. So, we wrote, so let us keep this intact. Zeta of s is one of our most favorite Dirichlet series, of course. Suppose I ask you, what is the square of zeta of s with itself? This would be equal to summation n going from 1 to infinity h of n over n to the s, where what is h of n? It is the Dirichlet convolution of 1 with itself. So, summation d dividing n f of d, which is just 1, times f of n over d, which is also just 1. So, this is basically the divisor function, right. Which we have given two notations, one is d of n, the other one is sigma sub 0 of n. Of course, you can do something similar with something similar for sums of divisors or sums of kth powers of divisors as well. So, this bit I leave to you as an exercise. So, in general, suppose you have sigma sub k of n, this is equal to the sum d raised to the k, where d runs over all the positive divisors of n. So, what is this actually equal to? This sigma sub k of n simply turns out to be the convolution of two functions f star g of n, where f of n is equal to n raised to the k and g of n is just the identity function, right. So, what happens here is, therefore, if you are going to write out the Dirichlet series corresponding to this sigma sub k of n over n raised to the s, this just turns out to be summation n going from 1 to infinity. The first term is n raised to the k over n to the s, that is your just your f of n, times summation n going from 1 to infinity 1 over n raised to the s. Okay. But notice you have to be mindful of where this is absolutely convergent. So, this series is absolutely convergent when real part of s minus k is greater than 1. This is absolutely convergent when real part of s is greater than 1. Okay. So, between 1 and k plus 1 you take the maximum. So, this is basically zeta of s minus k times zeta of s when real part of s is greater than k plus 1. In this domain, you can write the Dirichlet series corresponding to the kth power, sums of kth powers of divisor function as a product of zeta functions at two different values. This is also an important identity. One final identity before we close the class today is another function, namely the Euler Phi function, which counts the number of co-prime residue classes up to n, right. Now, in one of our previous meetings, we had learnt that phi of n can be written as summation d dividing n mu of d times n over d. And therefore, what is this? This is just a Dirichlet convolution of f star of g at n, where your f is just your Mobius function and g, what is g? It is just n itself, right. I think this identity is clear, right. So, therefore, if you want to write phi of n over n to the s, what do you have? You end up writing it as product mu of n over n to the s times the product times the sum n over n to the s. which is just 1 over n to the s minus 1. Okay, so the real part of s minus 1 must be greater than 1 for this series to converge absolutely. This of course converges when real part of s is greater than 1. So, in general you can take real part of s greater than 2 and you end up getting that this is equal to 1 over zeta of s. We just saw this, right? Once you write this out in terms of its Euler factors, this is just 1 over zeta of s times zeta of s minus 1 in the region when real part of s is greater than 2. So, this is another interesting multiplicative function which you have written as a whose corresponding Dirichlet series you have written as a product of two Dirichlet series. Okay. There are other examples and as the need arises we will study them. In particular, one very important Dirichlet series that we study is that which leads us to the prime number theorem. So, take the von Mangold function. So, this is here is an exercise for you. This series is absolutely convergent in real part of s's when real part of s is greater than 1. Okay. And the next thing I would like you to think about is this lambda of n, is it a multiplicative function? If it is a multiplicative function, what is the, can you write out the Dirichlet, the Euler product formula? So, this is quite important, and remember all of these things that we are learning is with a view to understand techniques to study partial sums of the concerned arithmetic function. Okay. So, here we are approaching average values from the point of view of complex analysis. This is the difference. Previously, we studied lambda of n's sort of like random variables, and we talked about expected value of the random variables, but in this case, and that approach works beautifully for additive functions. When you are talking about multiplicative functions, you bring some parallel techniques into the process. So, more about this next time and of course, today's live session. We will stop for today.